makes that the ABL will have very obvious diurnal variation. So this is also a very important part about ABL. If we recall what you have learned before, you must know that like temperature or moisture, maybe specific humidity or relative humidity. Can you still remember that usually they will have very obvious diurnal variation? For example, for temperature, usually we know that as the sun rises, the temperature will also increases, right? And maybe it will reach the maximum value during the early afternoon, okay, or maybe at noon. And then the temperature will decrease. And after the sun sets, the temperature will continue decreasing. And until in the early morning, the temperature will reach its minimum value, right? So that's a very obvious diurnal variation of the temperature. And this is a very good example to illustrate that usually ABL will have very obvious diurnal variation. Okay, so that's the second very important thing here. And the third thing is that, and most of you, I think, will remember, is that turbulent property of the atmospheric boundary layer, right? So I think maybe turbulent or turbulence, you will not forget, but don't forget about the first two very important parts, okay? Okay, firstly, it lies just directly above the Earth's surface, and also all the parameters like temperature, humidity will have very obvious diurnal variation, which means that it will happen or it will vary, has a very obvious principle during one day. So it's diurnal variation. Okay, so that's the definition of ABL. Then there's another question for you. Can you still remember what are the characteristics of ABL? Since we already reviewed about the definition of ABL, right? I think the characteristics of the ABL will be easier for you. So can you give me some keywords about the characteristics of ABL? Hi, Dinesh. Can you hear me? Dinesh, can you hear me? Or Inu, can you hear me? Okay, so my question here is what are the characteristics about atmospheric boundary layer? Other students, if you know the answer, you can also let me know. You can type in the chatting room here, or you can just directly speak it. Okay, no response. Maybe I will give you like first thing is that we can look at this slide. Okay, firstly, atmospheric boundary layer is the part of the atmosphere that interacts directly with the surface. Okay, so this is the first part that I have put much more emphasis on when we're explaining the definition of ABL. And also secondly, the flow in the boundary layer is generally turbulent. And the third thing is that the properties of the flow in the boundary layer depend on the properties of the surface. For example, the roughness. And fourthly, over land, the flow in the boundary layer usually will varies diurnally. That's what I have explained. For example, for the temperature, we will see very obvious diurnal variation. So usually, over land, the flow in the boundary layer varies diurnally, on the time scales that less than a day, So do you have any question about the characteristics and also definition of atmospheric boundary layer? Do you have any question? Okay, so if you do not have, I will continue. And in the last class, we also talked about answer. Do you agree with not use the microphone? You can just answer. And Kalani, do you agree with Cesaro? Okay, so can you still remember what that troposphere, stratosphere mean? Here, this is a picture here. Okay, can you see the troposphere? Okay, so this is troposphere. Now it goes to stratosphere, mesosphere, thermosphere. free atmosphere, free atmosphere. So that's the two parts about troposphere. And please remember that the height of the boundary layer will vary, but usually it will have an average value about 1 kilometer. Okay, and those that above the boundary layer is called free atmosphere. Free atmosphere. So can you understand this? I think this picture is more I think it's more good, it's better for you to understand. Okay, so we will have surface, okay, and generally the atmospheric boundary layer is about 1 kilometer. So this is called atmospheric boundary layer. And then we will have free atmosphere, okay, and the whole part, okay, from the surface to about 10 kilometers, we will call it troposphere. Okay, if we divide the troposphere into two parts, it will be free atmosphere and atmospheric boundary layer. Okay, and the boundary layer height is quite variable in time and in space, ranging from hundreds of meters to a few kilometers. But here, usually, we will think that it will have an average height about 1 kilometer. 1 kilometer. So I hope that you all can understand this. Okay, this is very important. That's the basic about the structure of ABL. Okay, and also from this picture, we can see that if we look into atmospheric boundary layer, actually we find that there's a surface layer that lies in atmospheric boundary layer. And usually the surface layer is about like several tens of meters. Okay, we will talk about surface layer in our following weeks. But here, I just want you to know that firstly, atmospheric boundary layer lies in troposphere. And secondly, troposphere can be divided into atmospheric boundary layer and the free atmosphere. Okay, so can you understand this? No question? Okay, so if you do not have, let's just continue. In the last week, we already talked about the history of boundary layer and turbulence. And in this part, we talk about the D'Alenberg's paradox. And here we just know that the paradox refers to that for D'Alenberg, he thought that the drag due to incompressible, inviscid potential flow on a body moving with a constant velocity is zero. But the observations does not inconsistent with his deduction. So this is called D'Alenberg's paradox. And in the whole 19th century, nobody can solve this problem. Okay, and until in 20th century, Prandtl introduced the concept of boundary layer. But from his theory, people found that actually the viscosity is also very important in the boundary layer, and the viscous forces in the boundary layer is comparable to the advective term. According to this conclusion, people found that, okay, this has solved the D'Alenberg's paradox, because in D'Alenberg's paradox, he thinks that the flow is inviscid. But until 20th century, people found that in boundary layer, the flow is viscous, is not inviscid. So the paradox has been solved. But from his research, he thinks that, or he thought that the boundary layer is a laminar boundary layer. Do you know laminar mean? Okay. So this video has shown us the laminar boundary layer means. Okay, so let's just look a little bit about this. Please remember that the flow shown here represents laminar flow. It's not turbulent flow.
These streamlines of water flowing in a channel are made visible with hydrogen bubbles generated by electrolysis. The flow is uniform and laminar. The fact that the timeline, the vertical patches of bubbles, remain perpendicular to the streamline shows that the unobstructed flow is free of vorticity.
And so this is laminar flow.
Here is the flow over a plate.
Over a plane.
The flow is two-dimensional and laminar.
Mm-hmm.
Upstream of the plate, the flow is still uniform, but in the fluid layers near the plate, the velocities are much lower and vorticity is present.
Okay, so this is laminar flow. Okay, according to Prandtl, he thought that the flow in the boundary layer should be laminar. But if we deduce from his theory, if we deduce the depth of the boundary layer, we found that boundary layer usually have a height about 1.5 centimeters. But according to what we have already known that the boundary layer usually will have the height about 1 kilometer, right? So the difference is too huge, it's very huge. And people finally found that the atmospheric boundary layer, the flow in ABL is not laminar. It should be turbulence. It should be turbulent. So until now, people began to know that the boundary layer flow is not laminar, but should be turbulent. And turbulence leads to much deeper boundary layers. That's why we usually will have the atmospheric boundary layer have 1 kilometers. That's the reason, okay? And the difference between laminar and turbulent flow is not small. It's not small. So that's the logic. That's the logic here. Okay. Firstly, from Prandtl's, we have solved the Edinburgh's paradox. Okay, and we know that the flow in the ABL is viscous. But for Prandtl, there is some flaw about his theory. He thought that the boundary layer, the flow in the boundary layer should be laminar, but finally we found that it should be turbulent. And that's why the atmospheric boundary layer can have the height as 1 kilometer. Okay, if the flow in the boundary layer is laminar, the height of the atmospheric boundary layer will be very small. Okay, so this this video just shows us about how the turbulence maybe looks like. But here, this is just a simulation. Okay, the boundary layer that develops on a plate that tolls through a water tank, and the flow is visualized using dye and a laser sheet. So here, in the last class, I think some of you have already saw this movie. And in this class, I will just play a short part about this, okay, to let you have much more deep impression about turbulence. Okay, so let's just watch a little bit about this. Okay, so please look carefully about this. Okay, this is just a representation of the turbulence. And if you can recall back about what you have just seen in laminar flow, you will find that these two kinds of flow are very different. Okay, I will stop here. And this video just give you illustration about what the turbulence looks like. Okay, and we can find that that's quite different as the laminar and turbulent flow. And please remember that the turbulence is the unique characteristics about atmospheric boundary layer. Okay, and it just looks like this. Okay, so that's about the review about what we have learned in the last week. So do you have any question? Or is there anything that you cannot understand? If you have, please just let me know. Okay, I hope all of you can understand the knowledge here. Definition of ABL, structure of ABL, characteristics of ABL. Okay, so if you all can understand, I will go on. So in today's class, we will continue finishing about the first chapter, and there will be the last part is about the development of ideas on turbulence. Okay, because we all know that people does not firstly get the right answer. Okay, they have come along a long way, get to know the answer that actually the flow in the atmospheric boundary layer is turbulent. So I will just help you to go over the history about the development of ideas on turbulence. And turbulence firstly was introduced in 1507 from Leonardo da Vinci. I think you must have heard this famous name. Okay, he has pointed out the word turbulence, and he even described turbulences. Okay, but at that time he did not realize that the air flow in atmospheric boundary layer is turbulent. He did not mention this, but he just has pointed out the word turbulence. Okay, from his description, we can find that turbulence is those that observe the motion of the surface of the water. Okay, look at the picture here, and which resembles that of hair, which has two motions, of which one is caused by the weight of the air, the other by the direction of the curves. Thus, water has adding motions, one part of which is due to the principal current, and the other to the random and reverse motion. So that's the original definition or description of turbulence from Leonardo. Okay, and we can find that until now, there are several keywords lies in his definition when we talk about turbulence. For example, eddy. I think you must be familiar with eddy, okay? Because you have learned eddy covariance measurement, right? You already learned this. And also, when we talk about turbulence, we usually will say that it is very random. random here. So Leonardo actually, his description is very important for us to understand or give us a vivid description of turbulence. Okay, so that's the early history. And then in 1883, okay, more than 300 years later, Osborne Reynolds, also a very great scientist, he described results of experiments on flow through pipes. Okay, he did such kinds of experiments by himself, and also he observed the flow pattern. And in 1895, he published a paper on the mathematical treatment of turbulence. And he introduced idea of separating the flow into mean and the fluctuating parts. And this is now known as Reynolds decomposition. Okay? I think you also may have already learned about Reynolds decomposition, right? And the basic idea for Reynolds decomposition is that the flow can be separated into mean and fluctuating parts. Okay, so that's a basic idea. And in chapter 2, we will also talk about the Reynolds decomposition and Reynolds averaging. Okay, so at that time, we will also mention about this. Okay, so that's an development of turbulence. Okay, and the experimental investigation of Reynolds is like this. Okay, he has done several different kinds of experiments, and here ABC just show 3 of them. Okay, he investigated the flow through the pipe. Okay, flow through the pipe, and the flow through the pipe was visualized using ink. Okay, just like using dye in the last movie. Okay, use ink, we can see the pattern of the flow. And for low speeds, the ink just followed a straight line as it was illustrated in figure A here. Okay, if the speed is very small, the ink follow a straight line. And for higher speeds, the ink rapidly spread over the width of the pipe, just as figure B shown. Okay, so at higher speeds. And can you guess what about figure C? And guess what happens? Okay, so for figure C, we find that the transition from steady to turbulent flow occurred above a critical Reynolds number. And for figure C, we found that actually for higher, even higher speeds, okay, the turbulence turns like much more like the turbulence. So from figure A to figure C, we can see a transition from steady to turbulent flow. Okay, and we usually will note that above a critical Reynolds number, okay, the flow turns from the steady one to the turbulent one. Okay, usually there will be a threshold, and the threshold is represented by Reynolds number. Okay, and usually we know that for turbulent flow, usually the Reynolds number will be higher. Okay, higher Reynolds number represent that the flow will much more likely to turn into turbulent flow. Okay, so this is the conclusions we got from Reynolds experiment. And in 1895, he published paper analyzing the above results. And this paper introduced Reynolds decomposition. That's what we have already mentioned. And also, Reynolds averaging has been used to derive what is now known as TKE budget, or turbulent kinetic energy budget. Okay, so this we will talk about this later in today's class. Okay. Okay, So I think we can have 5 minutes break. Yeah, we just have 5 minutes break and then we will continue our second class. Okay, so just take a rest. Okay, hello everybody. Let's just go back to our class. Are you ready?
Okay, Lavish.
Oh, okay. So, Lucinda, I can hear you speaking. So your microphone is okay?
Yes, Lavish. I think the problem is with my connection last time.
Okay, good. That's good. Okay, so we'll continue. In the last class we already talked about like a brief history about turbulence. And here we should know that there are two very important persons has promoted our understanding about turbulence. The first one is Leonardo, right? Leonardo. From his very brief description of turbulence, we have known some basic characteristics about turbulence. And also for Reynolds, his contribution is very big, very big. He has even laid, I think, most of the foundation about boundary layer meteorology because his Reynolds decomposition and Reynolds averaging are very important. And today we will also talk about this. Okay, but before we talk about chapter 2, there's last thing we should do. Let's just list a summary about the characteristics about turbulent flows. Okay, so when we talk about turbulent flows, can you tell me, firstly, can you still remember some of the characteristics about turbulence? Because I think you already learned the class about surface energy exchange, right? Mostly in that course, you will also be taught about turbulence, right? So can you still remember some of the characteristics about turbulence? Can you still remember some of them? Also, I have mentioned a little bit about this when I introduced about Leonardo's description. Can you still remember? Who wants to answer the question? Okay, so may I know that if you think atmospheric boundary layer is hard or easy for you to understand according to what you have learned? Can you let me know? Can you let me know what's your opinion about atmospheric boundary layer? Do you think it's hard or maybe it's easy? See, Sarah, can you let me know your opinion here?
For me, I think it's hard for me now.
It's hard, right? So since this course has just at the beginning, right? So you think it's hard, maybe it's because when you learn about the the earlier courses, you still think it's hard, right? Okay, so please do not worry. Do not worry. You should think that since you already learned some basic knowledge about it, right? And now in this time, we will also based on what you have learned and to like a kind of review, but we will also taught new topics. So this time, I hope all of you can take this as another chance for you to better understand boundary layer meteorology. Okay, that's very important for our major, for this major. Okay, so don't worry, don't worry. And if you can not understand it, please just interrupt me, and I will explain it for you. Okay. Okay, so here let's go back to the turbulent flows. I will list several characteristics about turbulent flows. Some of them maybe you have already learned before, but maybe some of you have never heard before, but that's all okay. Okay, you just take this as a totally new course here. Okay, so firstly, we do not have a very precise definition of a turbulent flow, but we can list several their properties. Firstly, velocities and other variables just fluctuate randomly in space and time. So from the first property, we should know that turbulence is very random. It's very random. Okay, this is also mentioned in Leonardo's description. Can you still remember that? Okay, this was also mentioned in his description. So here the first property of turbulent flow is that they usually varied randomly. Second property is that fluctuations occur on a wide range of length, scales, and frequencies. Right? So that's the second characteristics. The third characteristic or property is that the flow is three-dimensional and has high levels of fluctuating vorticity. Okay, so this time, the third property tells us that we should take turbulent flow as the 3D structure. So what we think or imagine there will be like 2D, right? But here, please remember that since it's a kind of flow that lies in the atmospheric boundary layer, and actually it should be three-dimensional. If it has coordinate, you should know that we can use x, y, z, three coordinates to describe it. So it's a three-dimensional structure. The fourth property is that turbulent flow dissipate kinetic energy through the effects of molecular viscosity. This, when we talk about TKE or turbulent kinetic energy budget, we will also talk about the dissipation. Here, you just to get this kind of like impression that, okay, turbulent flow will also dissipate the kinetic energy through the effects of molecular viscosity. Okay, we already talked about viscosity, right? And we already know that the flow in the boundary layer is viscous. So molecular viscosity is we can say that it is the only way for turbulent flow to dissipate the kinetic energy. Okay, we will also talk about it later. Okay, and then turbulent flows are diffusive. And turbulence is a property of the flow, not the fluid. Okay, it's a property of the flow, not the fluid. So these are the properties for the turbulent flows. And for each of them, please remember them. Okay, they are all very important. It has 3D structure and usually randomly fluctuated, and it will like vary or occur on a wide range of length, scales, and frequencies. Okay, I think each of the property we will encountered in the following weeks or in the following lectures. Okay, at that time, when we talk about one of the properties, please recall back when we talk about the turbulent flows here in today's class. Okay, so there has relationship. They have relationship. Okay, so for our course, okay, we will work on the turbulent boundary layers. And we know that we just introduced you about the work that has been done by like Reynolds or Prandtl, but what we should know is that the works on the turbulent boundary layer has continued until now. People still like doing more investigation about the boundary layer. So our understanding is still deepened. It is still deepened. And the atmospheric boundary layer is just one example of a turbulent boundary layer. And many of the results presented in these lectures originally came from engineering, particularly in aerodynamics. Okay? For example, when Reynolds did his experiments, he used pipe, right? So these are all the things that usually will be adopted in aerodynamics field, but we can get our understanding about atmospheric boundary layer flows from aerodynamics experiments. And one of the features of the atmospheric boundary layer is that the effects of buoyancy are often important. Can you still remember what does buoyancy mean? Can you still remember it? And it is related with the surface heat flux. Can you still remember that? Buoyancy, okay? We will also talk about buoyancy later, okay? And in this course, you will be introduced to the practice of the ABL and the theory that used to understand it. Okay, so do not worry. Maybe sometimes it will be a little bit difficult, but I will try to make all of you understand it. Okay, so that's the whole for chapter 1. Okay, chapter 1 is like an introduction. And in this introduction, there's still very important points here. And for today's class, you should know what are the characteristics about turbulence flows. Okay, so you should put much more attention to this slide, Okay, so that will be the whole for chapter 1. Do you have any question about this? Okay, so if you do not have, I will continue to open chapter 2. Okay, so we will continue. Okay, so can you see my PPT file here?
Yes, Lash.
Okay, good. So I will continue. Sorry, wait me for a moment. I will open the chat window so I can see what maybe you will send me some message. Okay. In today's class, we will talk about Reynolds averaging. Have you ever learned this part in surface energy exchange course or maybe in other courses? Have you learned this? Can you please let me know? You do not remember? Sitara, can you still remember that you have whether you have learned Reynolds averaging before? Or maybe Pasindu? Can you still remember whether you have learned this before? Can you give me some feedback? Inu or Dinesh, can you hear me? Can you still remember whether you have learned Reynolds averaging before? Okay.
I don't remember Lash.
Okay, good. Thank
But
you.
I remember the topic, but
Oh, you mean that maybe in the earlier courses, maybe Reynolds
yes, I
averaging.
only remember the topic, but
Okay,
not the information.
okay, I got it. Okay, so the answer from Dinesh is that we learned something about that, but now didn't remember anything. Okay, okay. So so you just take them as totally new. Okay, so for Reynolds average in this part, I just say that everyone, each of you can do Reynolds averaging. I just want to introduce you basic knowledge about like Reynolds flux. Okay, Reynolds flux. And what does Reynolds decomposition mean? And there are several important rules for doing Reynolds averaging. Okay, and after you have known this, okay, we can deduce the Reynolds average Navier-Stokes equations. And these equations, why we should learn these equations? That's because these equations are the basics for us to understand turbulent kinetic energy budget. Okay, so actually, chapter 2 is also a foundation for our further study. Okay, so here, firstly, let's just look at part 1. Okay, so this is just a review about turbulent boundary layer, since we already seen this video in the first class, so I will not play it again. Okay, I will not play. I will just skip this slide. Okay, in chapter 2, there are 3 contents, okay, or 3 parts. Firstly, we will describe Reynolds averaging, and secondly, we want you to understand what is Reynolds flux and what's its role in the boundary layer. And the thirdly, and also last but not least, is that we should derive the RANS equations. Okay, these equations are basics for us to understand the turbulent kinetic energy budget, okay, TKE budget. Okay, so let's just turn to the first part. Okay, and before we talk about the content about first part, here there is just basic knowledge about the coordinate. Okay, so what is shown here, x, y, and z, is a Cartesian, Cartesian coordinate. This is a kind of very classic coordinates, okay? And we know that usually for like the vector, velocity vector, and the scalar concentration gradient, okay, they are all generally expressed in a right-handed Cartesian coordinate frame. And in the discussion of like momentum, mass, and energy conservation, the frame's origin is really at a fixed point. For example, this is the fixed point. And the directions of its 3 axes, like x, y, z, are also fixed. And maybe the horizontal x-axis pointing to the east, and the y-axis pointing to the north, and the z-axis just align with and in the opposite direction of the gravitational force. So this is a very classic Cartesian coordinate. And everyone, since we told you that turbulence has 3 dimensions, right? 3 dimensions. So we should know that it means that we should use like x, y, z to describe it. So that's called 3D or 3 dimension. And here on the right of it, listed several conventions when we talk about, for example, the velocity vector v, okay, usually comprised about the u, v, and w, okay, and the gradient vector of a scalar quantity a, okay, can be written as like this: derivative of a along the x, right? Derivative of a along y, and derivative of a along z, okay? And also, this part is about pressure gradient force, right? Pressure gradient force. And it's also in 3 directions: x direction, y direction, and z direction. And for Coriolis force, okay, it also has 3 dimensions. But what's most important is that for z direction, we think Coriolis force equals to 0. So it just plays important role in x direction and in y direction. Okay, so this is some prior knowledge that you should know before we talk about the following part. Okay, so do you have any question about this? And also, in the micrometeorological coordinate, this is a very special type of Cartesian coordinate. We think that the lateral mean velocity component, which means that the V bar in the surface layer is always 0. And the long-term average of the vertical velocity W bar should also be very close to 0. Okay, so this is by definition here. So please remember them. Okay, so the first part that we will introduce you about the concept about Reynolds flux. But before we turn into Reynolds flux, firstly, I want all of you to see the time series of wind components here. Okay, it's for 3 directions, U, V, and W. And here, there will be a horizontal line here. Can you see it? In each picture, okay? This is the mean value. And compared with V and W, we find that the mean value of U, of this velocity part, is not 0, right? Because 0 is here. But for V and W, we can find that the mean value of them are usually close to 0. So this is what I have just said before. Okay, by definition, we think that V bar and W bar usually are very close to 0. Okay, but for U bar, it is not 0. Okay, for example, in this time series, the U bar equals to 3 meters per second, right? Okay, and for Reynolds decomposition, it really thinks that for U, it can be divided or can be separated as a mean and a fluctuating part. So actually, the capital U can be written like this. Okay, it's the sum of the U mean or U bar plus U prime. The prime means it's the fluctuation. And also that's the same for V and W. Okay, the capital V can be written like this. It's a sum of the V bar and V prime. And also W is the sum of the W bar and W prime. Okay, so can you understand this? This is Reynolds decomposition here. So it's not hard, right? Well, next time when we talk about Reynolds decomposition, you should know that it just means that the U can be written into 2 parts, a mean part and a fluctuating part. So this is Reynolds decomposition. And then if we combine 2 parameters together, for example, here, suppose the circle represents a puzzle here. And in this picture, the puzzle just go upwards, right? Go upwards. So this time, the W prime is bigger than 0 because the puzzle is moving upward. And let's just suppose that the X is a scalar. Maybe it's like CO2 concentration or other matters, okay? And this time, X prime is also bigger than 0. So the product of W prime and X prime will also be bigger than 0, right? In this picture. And if we look at the second one, we find that the puzzle is moving downward. So W prime is smaller than 0. And suppose the X prime is also smaller than 0. We will find that the product of them will be bigger than 0. So these first 2 conditions all generated or all lead to the product of W prime and X prime bigger than 0. Can you understand this? So it seems that the air with excess X moving up and air with a deficit of x moving downward all makes a positive contribution, right? A positive contribution. But if we look at the next two pictures, things are just on the contrary, right? This time, the parcel is moving upward, so W prime is still bigger than 0. But this time, X prime is smaller than 0. So the product of W prime and X prime is smaller than 0. And if you look at this one, we can also find that since the parcel is moving downwards, so W prime, with no doubt, should be smaller than 0, but X prime is bigger than 0. So the final result is that the product of W prime and X prime is smaller than 0. So that means the air with excess X moving down and air with a deficit of X moving up makes a negative contribution, which means that W prime X prime is smaller than 0. So this is what we can get from the picture here. So do you have question about this picture? If you have, please just let me know. Okay, so if you do not have, we will continue. And this time, this is also a time series, but pay attention here. The y-axis is no longer UVW. It's the product of U prime and W prime. And also for the bottom picture, the y-axis represents V prime and W prime. So that's the product of two velocity part or two velocity component, right? And this time, if we just combine them together and get the product, we can also plot the time series picture of this. And if we do the average of all the dots here, we can get that, okay, during the 15 minutes, from 0 to 15 minutes, the average of the U prime and W prime, the product of U prime and W prime is minus 0.2 square meters per second, per square second. Okay, so this is how we got the number here. Can you understand this? And also, if we do the average, do the time average during the 15 minutes about the product of V prime, W prime, we got the answer here. We got the answer here. And we found that actually the U prime, the average of the U prime, W prime is a negative value, right? And V prime, W prime is really a little positive value, okay? And this is also typical of boundary layer because the mean wind U is positive, and the physical reason for this relation will explain in our later lectures. But here, what you should firstly know is that this is a product of two parameters. And here in this picture, we just do the plotting about U prime and W prime, V prime, W prime. And if we do average, okay, for the whole 15 minutes, we can get the result. And please remember that we add a bar here, which means that this is an average, okay? And for V prime and W prime, this is also a bar here, which means that it's the average for the whole 15 minutes here. Okay, so can you understand this? Okay, so if you have no problem, let's just look at the Reynolds flux. Okay, so the average of W prime X prime. So here we can also replace this as V prime, W prime, U prime, W prime. That will all be okay. Okay, the average of the over all the puzzles gives the Reynolds flux of X. The Reynolds flux are in this form, a bar. There's a bar and W prime X prime. And actually, if you learn about the statistics, you will also know that this kind of format is also the covariance. We can also call it covariance between the fluctuations in the vertical velocity and the quantity x. Okay, so this is Reynolds flux, and also we can call it covariance between W prime and X prime. Covariance is from the statistics perspective, and from boundary layer meteorology perspective, we call it Reynolds flux. And we can replace X with V, with U, or with anything, any parameters. And if they're all in this kind of format, we can call it Reynolds flux. And here we have just considered obtaining the flux by averaging over time. So here, how we got the covariance of U prime and W prime, we just do the average of U prime, W prime over the whole 15 minutes. So this is a time average. Okay, this is just a time average. And actually, fluxes can be estimated by averaging over space. Okay, in this slide, we just average the Reynolds flux over time, but actually they can also be estimated by averaging over space. If, for example, using an aircraft, usually we know that the measurements were taken along the flight path of an aircraft, right? So if these are all instantaneous, so if we average them together to get one number, this is a kind of average over space, not over time, because all the measurements were taken at the same time. So doing averaging over time is meaningless. This kind of average is called averaging over space. But usually in this course, the average are usually doing by over time. For example, maybe half an hour, or maybe 15 hours, or 15 minutes, 15 minutes, or half an hour, or maybe 1 hour. This will all average over time, not over space. Okay, so can you understand this? Do you have any question about Reynolds flux? So if you do not have question, you can also type in the chatting room so that I will know your feedback. Okay, is that okay for you? Okay, thank you, Sarah. You have no question. What about others? Okay, good. Thank you, Pasindu. Okay, so if you have any question, just feel free to ask them out. Okay, so I can know that. Okay, so we have already talked about Reynolds fluxes. Then we will talk about the relationship between gradient and fluxes. Okay, so this time, let's just look at this picture. Here, the circle has still represent an L puzzle. And here, we just suppose that since the L puzzle is moving upwards, so the W prime is bigger than 0. So W prime is positive, and the X prime is negative. And usually it depends on the gradient of the scalar X. Okay, and here we just suppose that x prime is negative. And L, you can see the L here. L just represents the distance traveled, okay, of the x, okay, by the turbulent flow. So x is the distance. And the L is a property. The distance of L is a property of the turbulent flow. And usually it is being of the order of magnitude of the size of turbulent eddies. Okay, so here you just know that L is the distance and it has something to do with the property of turbulent flow. And we know that x prime, okay, have such a kind of relationship with the gradient of the scalar x. Okay, so it equals to x prime equals to minus L multiplied by the z derivative of the mean x, That's the relationship between x prime and L. And if we consider about Reynolds flux, what we have just learned before, okay, just learned, it equals to the k minus the gradient of x, okay, the z derivative of mean x. So this means that, so the k here is proportional both to the absolute value of w prime and also to L, okay? But from this part, we know that the flux is of the opposite sign as the gradient. So it means that the flux is down the mean gradient. And the K here is known as the eddy viscosity, and depends on the flow. More specifically, on the characteristic velocity and length scale of the turbulent eddies. Okay, so here what we want you to know is that this equation here, usually the flux is of the opposite sign of the gradient. Okay, it means that if the z derivative of x mean is bigger than 0, usually it means that the Reynolds flux is smaller than 0. Okay, they have such an opposite sign. And why it has the opposite sign? That's because of this. Okay, because x prime has an opposite sign of the gradient here. So that's why finally the Reynolds flux has the opposite sign as the gradient. So their relationship is on the opposite side. And let's get a summary here. The idea of turbulent fluxes or Reynolds fluxes is one of the key ideas in boundary layer meteorology. And we will show later that these turbulent fluxes affect the large scale or mean flow. Okay, so the turbulent fluxes will affect large scale or mean flow. We will show that the effects of turbulence on the large scale flow are a consequence of the non-linearity of the Navier-Stokes equations. So this part is part 3. When we using Reynolds decomposition or using Reynolds averaging to derive the RANS, we will find that actually the effects of turbulence on the large scale flow is a consequence of the non-linearity of Navier-Stokes equations. Okay, this will be proved in the third part about this chapter. Okay, so here just to let you know that. And finally, for our purposes, the important effect is represented by variations of the Reynolds flux in space, okay, in space. And it does not affect the large-scale flow, okay? If the Reynolds flux is uniform in space, it means that it does not affect the large-scale flow. Okay, so since we already learned about Reynolds flux, the relationship between Reynolds flux and gradient, the next very important terms is about flux divergency. And here there are very different sign about this, right? So actually, firstly, this format, the negative or the minus z derivative of covariance between w prime and x prime. This is called flux divergency. Okay, please remember that we will add a minus sign here. Okay, so this is flux divergency, and usually sometimes it will be bigger than 0, but sometimes it will be smaller than 0. And let's just look at each condition, okay, one by one. Okay, one by one. Here, there's something that first you need to understand. Firstly, in these figures, the fluxes are shown by the solid arrows. So these solid arrows means fluxes. So it means here, it means the average of w prime and x prime. Okay, it shows. And the arrows point in the direction of flux, which means that if look at this arrow, it means that flux is going upwards, right? And if for this arrow, it means that the flux is downward. Okay, so the direction. And thirdly, the length of the arrows are proportional to the magnitude of the flux. So the length. So compared with these two arrows, can you tell me which arrow means there has much more flux? This one or this one? According to the length of the arrows. The upper one or the bottom one? Can you let me know? Which arrow represents more flux? Okay, Kasindu, can you tell me? If we look at these two arrows here, which arrow represents more positive flux? Oh, good. What kind of function you are using? I just saw this blue circle here. Okay, that's great. That's great. Okay, because this one has a longer length, right? It's longer. So it means that it has much more flux. And please also remember that we just, by definition, upward pointing arrows represent upward fluxes. And these are by convention defined as positive. Okay, so compared with these two arrows, of course, this one has much more positive fluxes. Okay, so that's correct. That's correct. Okay, and also compared with this one. Firstly, these fluxes are negative. And if we look at the absolute value, we should know that this longer arrow means that the absolute value of flux is bigger than this one, okay? And if we look at these two parts, okay, we have more flux in and smaller flux out. We have more flux in and less flux out, even though we know that this one represents negative flux, but the net effect is also X accumulates in the volume, right? Because more in, less out, more in, less out. So the net effect is X accumulates in the volume. But if we look at the right part, things are just on the contrary, right? We have smaller one in, but bigger out, smaller in, bigger out. So the net effect is that X will decreases in the volume, right? So this is by looking at the 3 points here and by looking at the picture here, these are the conclusions we can get. Okay, for the left picture, X accumulates, but for the right picture, X decreases, right? So how we deduce about whether the flux divergency is bigger than zero or smaller than zero? Okay, how we got this? Let's just first take 5 minutes break and then we will continue our last class. Okay?
Okay, Raushi.
Okay, good. Okay, hello everyone. Okay, let's just begin our last class. Okay, last class for today's lecture. Are you all ready? Okay, so in the last class, we have already learned about what is Reynolds flux, right? So Reynolds flux actually has the format like W prime, X prime, and a bar here. This can be called Reynolds flux, right? And also in the last class, we know that the relationship between the Reynolds flux and the gradient usually has an opposite sign. And how we got this is because the X prime has a negative relationship with the gradient. Okay, so this is the most important thing that we have learned in the last class. And also we talk about the flux divergency here. So here, from the left picture, we know that no matter it's negative flux or positive flux, okay, for this one, this is the upward arrow represent positive flux, and the downward arrow represent negative flux. But no matter it's positive or negative, in this way, we just find that there's more in and less out. So actually the net effect is that X accumulates in the volume. And under this condition, we can find that if we just look at this, as the height goes up higher, the fluxes becomes smaller, right? Because this area is shorter than this area. So it means that the flux becomes smaller. So the z derivative of this should be smaller than 0, right? But here, there is a minus sign here. So actually, it becomes positive. Can you understand? So if we just look at this picture here, as the height goes up higher, this flux has become smaller because this area is shorter than this area, and also because it is upward arrow, so it means that the flux is positive. So actually, as the z becomes higher, the flux becomes smaller. So the z derivative of the covariance here should be smaller than 0. But because there's a minus sign here, so actually it is bigger, or it becomes positive. And let's look at this way. Okay, as the z becomes higher, this one, the negative one, even though it has like longer length than this one, right? But please remember, it means negative because the area is downward. So the absolute value is bigger. But since it has a negative value, so it means that as the z becomes higher, the fluxes becomes smaller. So this one should also be smaller than 0. But because there's a minus sign here, so the total effect is that it is positive. So can you understand? Can you understand why under these two conditions, they all have positive one? Can you understand this? You can give me some feedback. And it's okay if you cannot understand. Okay, both are okay, but just give me feedback. Dinesh, can you understand this? Or Sitara, can you understand this? Kasindu and Inu, can you understand?
Understood, Laosha.
Okay, so Sitara, can you like just explain it? Why this one should be positive? Can you explain by yourself? What about Pasindu? Okay, no response. I will just explain again, okay? So suppose the flux this arrow represent is A, and this flux represented by this arrow is B, okay? And also we know that this arrow are upwards, so A and B are all bigger than 0. Can you understand this? Okay, and also how to define whether A is bigger or B is bigger. We should look at the length of the arrow, right? From this picture, we know that A has longer length than B, right? So it means that A is bigger than B, right? And now we know that A and B represent the Reynolds flux here. So as Z goes up higher, okay, this is for Z, right? Along the height, the flux becomes smaller, right? So actually, it means that the Z derivative of the flux should be smaller than 0, right? Because as the Z goes up higher, the flux becomes smaller, right? But here, since there is a minus sign here, so finally, this one should be bigger than 0. Can you understand? Can you understand this? Give me some feedback. Thank you. Okay, can you give me some feedback? Okay, so this is for this condition. What about this one? What about this one? That's the same. Okay, that's the same. I will write it in another color. Suppose this was represented by C, and this flux was represented by B. But here, one difference is that the arrows are downwards. So it means that C is smaller than 0. D is smaller than 0. And how to compare which one is bigger or which one is smaller? We should look at the length of the arrow here. We found that actually C has longer length than D, right? But so it means that the absolute value of C is bigger than D, right? But because C and D are both negative value, so it means that actually C is smaller than D. Can you understand this? So this time, let's still look at the Z derivative. Okay, so this is still the direction of Z. As the height goes up higher, this time, the flux is become smaller. So that's why we still can get the final result here. Okay. Oh, okay. So I found that there's a question from Sarah, right? So in Sarah, she raised a question, I think very good. So can you explain again why we put a minus mark before the equation? Okay, so actually the minus sign is included because actually the tendency of the variable is due to the convergency, which means that it is minus the divergency. So you can think this is just by convention. Okay, by convention, we will add a minus sign here. And this way, okay, if this one I will change another color here. This whole part is called convergency. And since under this picture, we find that this one is bigger than 0. Is bigger than 0. It means that this is convergency. Okay, convergency. And in the in the right picture, we find that it is convergency. It is convergency. Can you understand this? And also, the gradient of the fluxes determines the rate at which the variable x changes in the volume of interest. So we can see that for the left part, it is converging, right? Because there's more in, less out. So this is a convergency of x. So x accumulates in the volume. And in the right picture, there's less in and more out. So this is a divergency. So x decreases in the volume. So can you understand? See, Tara?
Yes, sir.
Okay, what about others? Okay, so if you do not have any question, you can also try to explain why in this way the minus z derivative of the flux is smaller than 0. Can you explain it? Maybe Sithara, can you explain it? Do you want to try?
Which one, Lausha? Right hand side or left hand side?
Okay, so can you explain this? Can you see my mouse here? Can you explain this? On the right picture, why the minus z derivative of the flux is smaller than 0? Can you try to explain this?
The upward arrows smaller than 0.
You mean which
So
one?
for
Which one? You mean this one is smaller than 0, right?
upward arrows.
Maybe you can also use mouse to explain. I think everyone can have the right. You can try to do this. Can you?
Wait, Lausha.
Annotation. You can also add your annotation.
These arrows
Yes.
bigger than 0. Sorry, smaller than 0.
You mean the
So
arrows
from
represent is smaller than 0? Do you think so?
yes, yes.
No,
bigger than 0. Sorry, Lausha. Bigger than 0.
bigger than 0, right? Why?
Yes.
Why bigger than 0?
Because less flux inside and
You should
outer
look at the
flux is
direction.
bigger.
You should look at the direction of the arrow. The direction of
Yes,
the
yes.
arrow represent positive or negative?
Positive.
Positive, right? Because the direction of the arrow is upwards.
Upward.
Right? Yes. Great. Okay, you can continue.
So considering the length of arrows, the more length arrow is bigger than shorter one. So this one is bigger than this one.
Yes.
So flux become bigger.
You mean a flux gradient, right?
Yes, yes. Flux gradient become bigger.
Okay. And then?
So it represent this smaller than 0.
Yes.
So tendency of equation is divergency. Am I correct?
So you mean it means that divergence, right? Okay, good.
Yes, yes.
Yes, I think that's correct.
Am I right?
Yes, right,
Okay.
right. Okay, so if we look at the picture here, we find that actually first, the arrow are all upwards, which means that the value should be bigger than 0. And since this one is shorter than this one, so it means that the longer one has bigger flux than the shorter one. And as the Z goes up higher, flux also goes up higher. So it means that this part is bigger than 0, because as Z goes up higher, the flux also goes up higher. But because there's a minus sign here, so the total or the net effect is that it should be smaller than 0. And this is called divergency. And divergency leads to x decreases, okay, because it's divergent. So x becomes decreased. And what about this one? Who wants to try? Do you want to try? Hasindu? Hasindu, do you want to try? Or maybe Sitara, do you want to try again to explain this one? You can explain it by yourself. Okay, it will be much better.
You mean this one, Lausha?
Yes. The last one, not this one. The right one.
This one?
Yes. Can you try to explain it for us?
So downward arrows represent negative.
Yes.
So it means it smaller than 0.
Okay.
So considering the length of arrows, this one is bigger than this one because this is the higher. This one have higher length. So actually, C is higher to this side. Flux gradient become smaller. No, flux
Okay, so I
gradient
think
become bigger.
please remember that this is a negative value, and the length of the arrow just represent the absolute value. So suppose this is E, this is F. Now tell me which one is bigger. E and F, which one is bigger?
E,
Why? Why E is bigger than F?
I have no idea, Laush.
Okay, so if we just look at the length of the arrow, we absolutely will know that the absolute value is E smaller than F, right? But since E and F were all smaller than 0, so actually E is bigger than F. Can you understand? So suppose the E is 3, is minus 3, okay? And F is minus 4. So absolute value, it means that F is bigger than E. But since E and F are all negative value, so actually E is bigger than F. Can you understand this?
Yes, Laush.
So the length of the arrow do not take into the sign here. It just represents the absolute value. So of course, F is longer than E. So the absolute value of F is bigger than E. But E and F, because the arrow represent the upward the downward, so E and F is negative value. So actually E is bigger than F. And also you should not use this direction. For Z, we drew the Z is always upward. So we can find that as the Z becomes higher, E is also higher because E is bigger than F. So without the negative sign, this one is bigger than 0. But if we put the negative or the minus sign here, it should be smaller than 0. So can you understand this? Can all of you understand this? Okay, I hope all of you can understand why we got this. Okay? Right? Okay, so we will continue. This is called flux divergency or flux inconvergency. Okay, convergency and divergency. Okay, and finally, we should know that the gradient of the fluxes just determines the rate at which the variable x changes in the volume of interest. Okay, so that's the final point here. Okay, then let's go to some common conventions or conventions about common fluxes, since we already encountered W prime X prime or V prime W prime. So what really does this mean? Okay, I will tell them one by one. Firstly, next time when you see this kind of format, it means x momentum flux. Okay. And for v prime, w prime, it means y momentum flux. And for w prime and theta prime, it means heat flux. And theta means potential temperature. Potential temperature. Can you still remember potential temperature? Okay. So usually we will use potential temperature, and the covariance between w prime and theta prime is called the heat flux. Heat flux. And then for moisture flux, we will use w prime and q prime. Q prime. Q is the specific humidity. I will type it in the chatting room here. Q is specific humidity. And we usually will also use latent heat flux. So here we will add L here. Okay, L is the evaporation constant here. So this is called L is the latent heat of condensation of water. So if we add L, okay, on the moisture flux, we will get latent heat flux. And L means the latent heat of condensation of water. Okay, so you can write down them. Okay, you can write down them. I'll add it as your note here. And sometimes it is common practice to refer to the covariance on the right, like this. Okay, by the same names, even though their dimensions are not correct. We will follow this practice in this course. So why we should add like rho, air density, Cp, the specific heat of air at constant pressure, or we should add L? That's because we want their dimensions to be right. But sometimes for simplification, we will just use the simplified fluxes here. Okay, for example, U prime, W prime, we see this represent X momentum flux. V prime, W prime represent Y momentum flux. And W prime, theta prime just represent the heat flux. And W prime, Q prime represent moisture flux. So please remember that. But if you need to take into like calculation, you should add them together because that can make your dimensions to be right. But for simplifications, usually we will use this simplified covariance format to represent momentum flux, heat flux, moisture flux. Okay, so can you understand this? Okay, so if you do not have question, we will continue. So let's go to the second part. We're going to talk about Reynolds decomposition. And here, before we talk about the Reynolds decomposition, firstly, we must define a large-scale flow. Okay, these are the two very typical synoptic charts. I'm not sure whether you have met this before, but here we can find that this is isobar here, and we can find a high pressure system here, right? High pressure system, and in this picture, we can find a low pressure system here. So for us, the mean flow will usually be the synoptic scale flow. So the mean flow equals to synoptic scale flow. Like for example, in those days, we're under the control of a high pressure system. So this is the mean flow. called or we can call it synoptic scale flow. And clearly, compared to the rapid variations in turbulent winds, the synoptic flow varies slowly. So because we already know that Reynolds decomposition just divide the U into mean and fluctuating part, right? So we should firstly know what does the mean flow represent. And usually the synoptic scale flow represent the mean flow, and the fluctuating part has very unique characteristic in that it will have very rapid variation compared with the mean flow. And this scale separation is important for properly defining a mean flow and a turbulent departure from it. Okay, so this is the basic. Then let's just look at the Reynolds decomposition here. The flow is divided into a mean and fluctuating part, which means that like this. Okay, for the three velocity components u, v, w, we can write them as u bar plus u prime, v bar plus v prime, w bar plus w prime. And also for potential temperature, we can also write it into two parts, the theta bar and the theta prime. Okay, so no problem here. This is called Reynolds decomposition. And the over bar denotes the mean, and the prime just denote the fluctuations. Okay. And actually, there are a number of ways to define the average, but averaging method must satisfy a number of conditions. And the simplest averages, no matter it's in space or time, only satisfy these conditions if the mean flow varies on time and space scales that are much larger than the time and space scales of the turbulent fluctuations. So here, please remember that for defining a mean flow, we should always keep in mind that the mean flow varies on time and space scales that are much larger than the time and space scales of the turbulent fluctuations. If this requirement can be met, okay, there will be no problem for us to do the Reynolds decomposition. Okay, so that's a very important requirement here. If we can meet this, it will be no difficulty for applying Reynolds decomposition. And here, let's just go back to the synoptic scale flow here to remind ourselves about the time scales of the mean and the fluctuating flow. Please note that in this upper graph, the time duration is just 15 minutes. It illustrates the turbulent wind fluctuations, and those fluctuations occur just on time scales of seconds. But the average on which they are superimposed does not appreciably change in 15 minutes interval. So which means that the mean does not change in the 15 minutes, but the fluctuating part just change every second. So this condition means that the mean or the synoptic flow has a much larger time scales than the fluctuating part. Under this condition, we can do Reynolds decomposition here. Okay, and in the weather charts at the bottom, these two weather charts here. On the other hand, the time scale for the evolution of the winds whose characteristics can be inferred from the isobars, is of hours or even to days. Hence, the practice that the Reynolds averaging must have to be well posed are satisfied by a wide margin, which means that under this kind of mean flow, since the variation of it are usually from hours to even days, so the fluctuating part of the Reynolds averaging can be satisfied by a wide margin. Okay? Less than hours or even less than days, it will also meet the requirement here. So here, just please remember that if we want to do the Reynolds decomposition, we should make sure that the fluctuating part has much smaller time variation range than the mean flow. If this condition can be met, we can do Reynolds decomposition here. Okay, so do you have any question about this? Any question about this? Okay, so if you do not have question about Reynolds decomposition, we will further introduce you about some properties of the averaging operation. So there are 5 properties. Okay, we can look at them one by one, or you can just quickly go over it. So the practice of the averaging operation is that first, the average of an average is just the average, which is shown here. The average of an average equals to the average. And secondly, the average of fluctuations is 0. So, for example, here, A and the capital A or capital B just represent like velocity or maybe scalars. Okay? It just represent any of them. And here, the average of the fluctuation equals to 0. And third, the average of the sum is the sum of average. So they equals to this. The average of the sum equals to the sum of the average. And fourthly, the average of the product of an average and the fluctuation is 0. So it's like this. The average of the product of an average and the fluctuation equals to 0. And the last one, which is also important, the averaging operation commutes with derivative like this. Okay? The averaging operator commutes with both temporal and spatial derivatives. Means the average of a derivative is the derivative of the average. Can you find them? The average of a derivative is the derivative of the average. Okay? So actually they are the same. So these 5 properties are very important for us to deriving the RANS equations. Okay, we will use the properties of this averaging operation when we derive RANS. So that's why we should first tell you about them. Okay, so actually these 5 properties are not hard, right? Are not difficult. Okay, you only has to remember them. Okay, and next time if you have to do Reynolds averaging, you should use them. Okay, this can help you to simplify your deduction. But here in our class, okay, you do not need to do Reynolds averaging by yourself. You should just know that, okay, what is Reynolds decomposition? What's the condition that it should be met? And what are the 5 properties about using Reynolds averaging. Okay, you just know them, it will be okay. Okay, you will not be asked to do the deduction by yourself. Okay, you will not be used them. Okay, so since we already know about the Reynolds decomposition, Reynolds averaging, we then can derive the RANS or Reynolds average Navier-Stokes equations. Okay, we can call it RANS. And firstly, in this part of lecture, we will obtain equations that describe the mean flow. And in the derivation, we will not neglect the products of the fluctuations in the flow, which means that during the process, when we derive the RANS, we will also have a byproduct, that is the fluctuations. Okay, it is because of the linear approximation here that we will also have a byproduct about fluctuations. And the whole result will be Reynolds averaged Navier-Stokes. Okay, and we will, since that will be take a lot of time, so in today's class we will just stop here. Okay, in the next class we will begin with the derivation of RANS. Okay, and after today's class, okay, please review what we have learned. Okay, since Mongolian meteorology is not that easy, but I hope that what we have learned, or what you have learned from this course, is the one that you really can understand. Okay, I will control that it will not be that so hard, but what I'm talking about, I think you should all understand. Okay, and since this is just the first 2 classes, first 2 lectures, okay, I think you still have time to catch up, okay, what you have learned. Okay, and today I have also record the classes, and I will send them to Pasindu, okay, to you by your email, and please share it with all your classmates, okay, because there are still many students that cannot join the meeting with us. Okay, so I think we will stop here. Okay, if you have any questions, just let me know. Okay, so thank you for your cooperation, and we will stop here, and have a good day. See you next week. Okay,
Thank you, Laoshi.
okay, thank you all.